There's only one group of order 1979. And by that, I mean that any two such groups must be isomorphic. Well, how could I possibly know that about such a large order? After all, you may recall that in the last group theory program, we looked at groups up to order 6, and we saw that for such small numbers even, it was quite possible to find more than one non-isomorphic group of a particular order. In fact, if we continued this and gone down to just groups of order 8, we would have found there were 5 non-isomorphic groups of order 8. Well, the fact that there's only one group of order 1979 is a consequence of Lagrange's theorem. And it's Lagrange's theorem that we're going to look at in this program. In fact, later in the program, when we come to state Lagrange's theorem, we'll see that it enables us to completely describe groups of infinitely many orders.
Lagrange's theorem hinges on the idea of cosets. What is a coset? If we've got a group G and a subgroup H, then to form a coset, we choose some element little g of the group. Its coset, which we denote by G capital H, is the set of all elements of the form little g times little h, where little g is the chosen element and little h is any element of the subgroup. Before we see how cosets fit into Lagrange's theorem, we'd better make ourselves familiar with the idea of cosets. So what I'm going to do is to take a group you're familiar with, choose a subgroup of that group, and form all its cosets. The group that I'm going to take is the group of all symmetries of the regular hexagon. We can represent this group by the different ways in which we can reposition the hexagon so as to occupy the same place. To help us keep track of where we are, I'll put a distinguishing black dot at one vertex. When the hexagon's in its initial position, the black dot will be at the top vertex. The initial position corresponds to the identity element of the group. So we have this symbol for the identity element, the hexagon with a black dot showing at the top vertex. Other symmetries include a number of rotations. For example, the rotation through a sixth of a revolution, the rotation through a further sixth of a revolution, and so on. In all, there are going to be 5 rotations like this, and then the 6th will return the hexagon to its initial position. Our symbols for the rotations are therefore these. The black dot now occurs in each of the 6 positions of the vertices. In addition to rotations, we have a number of reflections. For instance, if we reflect in this line, you can probably see the hexagon will occupy the same position. Now remember, to model reflections, what we do is we turn the hexagon over, like this. On the reverse side, the distinguishing dot is white. So whenever a reflection is involved, it's going to be the white dot that's showing. There are in all 6 reflections corresponding to the 6 positions the dot can occupy on this side. To be more precise, the 6 reflections are going to be these. We'll have 3 reflections in lines joining opposite vertices, and also 3 reflections in lines joining midpoints of opposite sides. So here are symbols for the reflections. And now we've got the whole group, the group of 12 elements. Our convention is that to represent the group element, which is a symmetry of the hexagon, we're representing it by the colour and position of the distinguishing dot. So there's our group. Now what about a subgroup? Well, let's consider this slightly modified figure. I've got the hexagon as before, but now I've added in one diagonal. Now the symmetries of this new figure form a group, because we know the symmetries of any figure form a group. Now any symmetry of this figure is going to be a transformation which leaves the hexagon fixed and also leaves the marked diagonal occupying this same position. Well, in particular, it leaves the hexagon fixed and therefore is a symmetry of the hexagon. And consequently, the symmetry group of this figure is a subgroup of the symmetry group of the hexagon. All symmetries of this figure will be elements from here. Now, what are they? Well, we're looking for those symmetries of the hexagon which leave the marked diagonal in this position. Certainly, there's the identity element, the initial position. we'll also have a rotation. The rotation through a half turn will take the line right round and bring it to the same position. In addition, there'll be two reflections. Reflection in this line, the marked diagonal itself, you can probably see will fix the marked diagonal, and also reflection in this line, the line perpendicular to the marked diagonal. Let's do that second one to check. We'll be reflecting, so we turn over like that, and you'll notice the line comes back to the same position. So our subgroup will have these four elements. I can pick which four elements they are from our list of all the group elements, but to help me to do this, I'm going to mark in the diagonal in question. I'm only going to mark it in dotted because, remember, it's not part of the hexagon, it's just there to assist us. The subgroup will be those elements in which the marked diagonal is in its initial position, which was at this angle. If we call the subgroup H, I'll give its elements names: H1, H2, H3 and H4. Now, which elements are they? They're going to be the symmetries of the hexagon which leave the marked diagonal in its original position, which was this position. I can pick them out. Here's the one, that's the identity element. Here's another, the rotation through a half turn. And there are two reflections. Here's one of them, and here's the final one. So these will be our elements: H1, the identity element, H2, the rotation through a half turn, and then two reflections. There's H3, and there's H4. So there's a subgroup. Now what about a coset? What we have to do is to choose some element of the group and form the set which consists of all the products G little h, our chosen element G, H running through all elements of the subgroup. So let's do that. I first of all want to choose an element of the group. I'll take this one, the rotation through a sixth of a revolution. If we call that the element X, its coset, XH, is just this set of four elements: XH1, XH2, XH3 and XH4. So we want to work out what those four are. Now the first one is no problem. Since H1 is the identity element of the group, when we compose anything with the identity element, it leaves it alone. And so XH1 is just X itself. Here's X, so I'll bring that down here. Now what about XH2? Well, let's just recall the conventions. This means that with the hexagon in its initial position, we first apply H2, and then to the outcome we apply X. So let's do that. The hexagon in its initial position, we first of all want to apply H2. Well, if we look along here, we can remind ourselves what H2 was. It was the rotation through a half turn. And then we want to apply X, rotate a further sixth of a revolution, which takes us there. So that's the element XH2. Here it is. Similarly for XH3, return the hexagon to its initial position, apply H3. We can see what will happen then from here. We'll end up in that position, so let's move there. There's H3. We then apply X, rotate through a sixth of a revolution, taking us there. Here's XH3. And finally for XH4, well, you probably realise now there's a shortcut. We can go directly to the H4 position, that's this one, and apply X. Rotate through a sixth of a turn, taking us there. Here it is. There's XH4. So there's our first coset. All it is, it's a subset of the group, a subset of four elements of our original group. Now the definition of coset tells us we can form a coset for any choice of element of the group. There are 12 in all, so there's several others we can choose. I'll work through another example of a coset, and this time I'll take a reflection. The identity position. This time let's look at the reflection in the vertical axis. That one. If we call this the element Y, its coset, YH, is this set of four elements. YH1, YH2, etc. What are they? Well, again, YH1 is no problem. Since H1 is the identity element of the group, YH1 is just Y. Here it is. What about YH2? Well, as we did with X, you can probably see how we can work that out. Taking this model, to work out YH2, all I want to do is to apply Y to the H2 position. So going to the H2 position, which is there, we apply Y, which was reflection in the vertical axis, giving us that. Here's YH2. And similarly for YH3, go to the H3 position, apply Y, which was reflection in the vertical axis, gives us this. There's YH3. And finally for YH4, the H4 position, apply Y, gives us this. Oh, that's lucky. It's the last element. And that's one thing I want you to notice from this example, the way in which we've now used up all the 12 elements of the group. The 12 elements have been used to form these 3 cosets. Yes, 3 cosets. Although we've only worked out 2, the cosets XH and YH, the subgroup H is itself a coset in an obvious way. It's the coset H1H, where H1, you'll recall, was the identity element. Why is that? Well, combining anything with the identity element, it just leaves it alone. So, for instance, H1 times H3 is just H3. And similarly for each of the elements. The coset H1H is the subgroup H itself. There's a second thing you've no doubt noticed, and that is, throughout each of these cosets, the marked diagonal has ended up in one and the same position. Throughout the subgroup, it was in this position. In the coset XH, it always ended up vertical. And in the third coset YH, it was in this position. Well, there are a lot of other cosets we could form. The definition of a coset tells us we can form a coset for each choice of element of the group. The group has 12 elements, so we could form 12 cosets. We found 3, so there are 9 more that we could investigate. But it's not difficult to see that for any other coset that we care to form, it'll have to turn out to be a repetition of one of these 3. Why is that? Well, let's suppose that we choose an arbitrary element G and imagine what happens when we form its coset. What do? As you saw with the examples of XH and YH, for our chosen element G, we simply apply G to each of these 4 positions in turn. Now, in each of these 4 positions, the positions of the subgroup, the marked diagonal is always in this same position, its initial position. So as I apply the element G to them, whatever G is, it'll do the same to the marked diagonal in each case. It starts in the same position, G will take it to a new position, but the same position in each 4 cases. So in the coset GH, the marked diagonal will be in the same position throughout. But there are only 3 positions for this diagonal. There are only 3 diagonals of the hexagon, the 3 that we've seen illustrated in these cosets. So any other coset must be a repetition of one of these 3. Now, of course, the elements may turn up in a different order, but that doesn't matter. The coset is a set, and as a set of 4 elements, any new coset must be a repetition of one of these 3. So the real message is this. The cosets of our group have partitioned the group into distinct subsets of 4 elements. And in fact, this will happen in general. For any group and any subgroup, the cosets of the subgroup always partition the group. And in particular, if we look at a finite group, then each coset will also turn out to have the same number of elements as the subgroup. So cosets partition a finite group into subsets of equal numbers of elements. And that's the basis of Lagrange's theorem. But before we move on to look at that, let's look at one more example of how cosets partition a group.
I'm going to take the same group, the symmetry group of the hexagon, but a different subgroup. As my subgroup, I'm going to take the symmetry group of this figure. It's just the hexagon again, but with this arrow triangle drawn inside. Well, what are the symmetries of this figure? First of all, notice that we can't have any reflections, because if we do a reflection, we get the triangle going the other way around. The symmetries are, in fact, just the identity, a rotation through 1/3 of a revolution to here, and through 2/3 of a revolution to here. Once again, we can mark our triangle into our hexagon and carry it around with us when we form the symmetry group of the hexagon. And we can pick out the subgroup. It'll just be those elements which have the triangle in its initial position. And to save time, we've already written this down. This is our subgroup, these 3 rotations. Well, that's our subgroup. What about our cosets? As before, we'd expect the cosets to be determined by the end position of this triangle. And if you think about it, you'll see there are just 4 positions that this triangle can occupy. I'll show you what they are. There's this position. That's the position the triangle has in the subgroup. There's this position with the point at the top. And the 2 positions we get by reflection. This position and finally this position. In the last 2 cases, you'll notice the triangle's going the other way around. Now, each member of our group is going to take the triangle to just one of these 4 positions. So using just this fact, we can partition up the group. And this is what we get. What we've done, this set is just the elements of the group which take the triangle to this position. This set's just the elements of the group taking the triangle to this position, and so on. Well, if the same thing happens this time as happens last time, we'd actually expect these to be our cosets. We'd expect that if we take these as our little g in the definition and compose it with the subgroup H in turn, that as our cosets we expect to get these sets. Well, let's just see if that's so. Let's take an example. In the first case here, if we take this as our little g, that's just rotation through 1/6 of a revolution, and then composing that with H, we expect the subgroup, we expect the coset rather, to be just this set here. Well, let's actually try that. First of all, take the first element of H. Now, we've got to follow that by little g, which is follow that by rotation through 1/6 of a revolution. We get that element. It checks. Let's take the second element of H, follow it by 1/6 of a revolution. We get that element. Finally, the final member of H, follow it by 1/6 of a revolution, and we get that. So indeed, you see that we do, as a coset, get this set as we expected. And a similar sort of argument would show that the other 2 are cosets as well. Well, what have we done? Once again, we've partitioned the 12 members of our group, this time into 4 cosets, each with 3 elements. So once again, you see, cosets partition a finite group up into subsets of equal numbers of elements. Well, we're not claiming to have proved that fact. We've simply shown that it's true for the 2 examples we've taken. But you'll find a general proof of that fact in the unit, and you'll see that it's true for any subgroup of any group.
So what? Well, suppose that I find a subgroup of order 7 for this group. What would its cosets look like? Well, we know the subgroup itself would form 1 coset, so I could pull the 7 elements of the subgroup down here as my first coset. And that'll leave me with 5 elements. Well, now any further coset has to be a distinct set of 7 elements. I can't get one. There's no way that I can partition the 12 elements of this group into equal sets of 7 elements. So what's gone wrong? Well, nothing's gone wrong, except for the assumption I made that I could find a subgroup of order 7. I simply can't do it. The problem being that 7 does not divide 12. To get the partitioning effect into cosets, the order of the subgroup must divide the order of the group. And that's Lagrange's theorem. For any finite group G and subgroup H, the order of H divides the order of G. Well, it doesn't look like much of a result, a simple arithmetic property relating the order of a subgroup to the order of the group. But in fact, it turns out that this is a very powerful result in group theory. And to illustrate this, in the remainder of this program, we'll look at just a few of its applications. First of all, what additional information does it give us concerning the group that we've been looking at? The symmetry group of the hexagon has order 12. So Lagrange's theorem tells us it might have subgroups of orders 1, 2, 3, 4, 6 and 12, for these are the integers which divide 12. But Lagrange's theorem also tells us that it can't possibly have subgroups of any of these other orders, 5, 7, 8, 9, 10 and 11. And we can take this idea further. Let's suppose that we're given a group of order 24. Well, in fact, there are quite a lot of groups of order 24, a lot of different ones. You've met one already in the course, the one we call S4, the group of all permutations of 4 symbols. It has order factorial 4, 24. Now, Lagrange's theorem tells us straight away that it might have subgroups of orders 1, 2, 3, 4, 6, 8, 12 and 24, but no others. We say that it might have subgroups of these orders. Lagrange's theorem doesn't tell us that it must have subgroups of these orders, only that these are the orders which will allow the partitioning effect that we've seen happens. As it turns out, S4 does have subgroups of each of these orders, but in the correspondence text you'll find an example of a group of order 12 which, despite the fact that 6 divides 12, this particular group does not have a subgroup of order 6.
Well, how does that help us with our group of order 1979? Well, you see, 1979 is a prime number, which means it doesn't have any factors, except, of course, for 1 and 1979 itself. So we know immediately from Lagrange's theorem that any group of order 1979 can't have any subgroups, except, of course, for the trivial subgroups of order 1 and the whole group itself. Well, that doesn't prove that there's only one group of order 1979, but it's the key. The trouble with 1979 is that it's a little too large to handle. So let's see how the argument goes with a smaller prime number, 5, say.
As 5 is a prime number, a group of order 5 can't have any subgroups apart from the identity subgroup and the whole group itself. Let's take an element G which isn't the identity. We know from this week's work that G generates a cyclic subgroup consisting of all its powers, G squared, G cubed, G to the 4th and so on. Now G isn't the identity element, and so the subgroup it generates can't be the identity subgroup. It must therefore be the whole group. But that says that the group is cyclic, and if you remember, that means that G to the 5th is the identity. And we know that all cyclic groups of a given order are isomorphic to the integers under addition modulo that order. So any group of order 5 is isomorphic to the group Z5. You can use an argument like this for any prime number. In particular, we can use it for the prime 1979. Let's just go through the argument again. If we've got a group G, whose order is P, where P is a prime number, then Lagrange's theorem tells us that this group can't have any subgroups except for the identity subgroup of order 1 and the whole group itself. So if we choose any element little g, which is not the identity element, we can form the set of its powers, which we know forms a subgroup, which we denote like this. What is this subgroup? It's not the identity subgroup, so all it can be is the whole group. Now this means that the group G is cyclic, generated by the element little g, and from this we deduce that G is isomorphic to the group ZP.
So now we know all about groups of order 1979. There's only one, the cyclic group. And in fact, for any prime order, there's only one group, the cyclic group. Well, of course, there are infinitely many prime numbers, so we know all about the groups for infinitely many orders. Not a bad day's work.